So thank you. I'm Scott Collenburg, and I'm going to cover what's in the climate change report in regards to freshwater fish. But I thought it may be interesting and help spark a connection from others inside the department doing permitting within land use, stormwater management, or anywhere else. If I went over some of the climate change related projects that we're doing and help talk about some specifics. But first, when we talk about climate change and impacts on the biotic community, I want to touch base on the anthropogenic impacts and challenges that predispose fish populations to stress and decline. So it's pictured in the middle of the screen is a distribution map of one of the most iconic freshwater fish species on the East Coast, native to the Appalachian Mountains, New Jersey state fish, brook trout. Very important culturally and economically, this map shows how brook trout have been reduced in many states, and New Jersey, being the most densely populated, is no exception to this. But trout are not the only fish species that has been negatively affected by human impacts in New Jersey. Sensitive fish species such as the bridle shiner, iron color shiner, comely shiner, slimy sculpin, just to name a few, have seen drastic changes in their distribution because of similar impacts. So climate change will work to potentially make these impacts even more pronounced on species like this that are most sensitive. There's a total of 90 species of freshwater fish that can be found in New Jersey, 60 of which are native. And I wanted to briefly touch on what makes them uniquely susceptible to climate change. So two of the main reasons is that temperature and precipitation have direct effects on the physiological and biochemical processes that regulate fish performance and survival. So because fish are exotherms, they can't regulate their body temperature through physiological means. Increase in air temperatures can manifest in the form of reduced growth, reduced food consumption, difficulties maintaining internal homeostasis, or influencing timing of spawning and migrations. Also, changes in hydrological conditions, such as extreme precipitation events that bring toxicants and pollutants into the waterways, will negatively impact fish inhabiting those streams in a similar fashion. Another thing that makes them uniquely susceptible to climate change is that they're confined to aquatic habitats, and movement to alternative habitats is often more restricted compared to terrestrial systems. So that's especially true in New Jersey with historical impacts that have fragmented waterway connections. So due to changes in climate and water quality, we're expected to see impacts to our fish populations, especially on cold water species. So as you can see from what's pictured to the right, and the statement that the majority of current cold water fisheries are projected to be warm water fisheries by 2100, regardless of climate scenario. However, I'll be sharing some of the recent work that we've been doing that sheds a more optimistic light on this projection and how we're identifying more resilient habitat than is being shown through larger scale modeling like this. In terms of water qualities, thermal and stream flow regimes will be altered and in turn affect physiological function of fish species. Time of life history events, such as American shad that migrate up the Delaware River in the spring, we may begin migrating earlier because of warmer spring and summer temperatures. They're already seeing this in the Columbia River, where American shad also migrate up in the Pacific Northwest right now. The toxicity of pollutants to fish generally increases at higher temperatures. There's been studies on bioaccumulation that have shown a positive correlation between temperature and the uptake of anthropogenic mercury and natural pollutants. We also may see something like a temperature oxygen squeeze in lakes that typically become stratified in New Jersey. As warmer water in the upper part of the lake or epilymnium gets thicker, dissolved oxygen decreases in the lower layer of the lake. So here we're talking about available habitat shrinking, and there could also be a complete loss of this area that some species heavily rely on. Sea level rise will have a significant effect on coastal waters, primarily by means of loss of freshwater habitat due to saltwater intrusion. This might have impacts to anadromous fish migrations and low-lying coastal plain waters associated with pine barren fish assemblages, such as black banded sunfish, banded sunfish, mud sunfish, and pirate perch. Generally, impacts to sensitive species will be greater than those that are more generalists, that have a wider range of water quality parameters that they are adapted to. So next, I wanted to talk a bit on projects that the Bureau of Freshwater Fisheries has been working on to address climate change issues. And one major project that started in 2018 was to begin identifying resilient cold water habitat by using continuous temperature monitors. Sites selected were mostly in places where we have documented brook trout in the past. Also, the modeling that we've done was adopted from research that is being done out of the USGS Leetown Science Center. It's based on the idea that prior modeling projections assumed that changes to cold water habitat would be spatially uniform across the landscape. But we know that's not true because a large driver of stream temperature in headwater streams is groundwater, and groundwater itself is spatially complex. And it also has the ability to buffer streams against the effect of air temperature increases. So that goes to the first statement here of the resilience of cold water habitat and headwater streams being more strongly linked spatially than temporally. So how do we understand groundwater influence? Well, the right way would be to build a heat budget model, but that can't be done everywhere. It requires a lot of data and time, but we can understand groundwater influence by building models that incorporate a groundwater metric that estimates the amount of influence based on relationship between air and stream temperature. So what's being shown to the right here in these graphs is when we have a site with low groundwater influence, we have very tightly dovetailed relationship between air and water temperature. And then in these high groundwater sites, like you see in the bottom graph, you see more invariance to air temperature. And this is a sign at this specific location that has more resilience to changes in air temperature over time. So we can create models and we can extract or infer how much groundwater is at each site and use this to identify resilient cold water habitat across the state at known brook trout locations. So we think this approach is much better at identifying cold water habitat than large-scale modeling efforts in the past that didn't incorporate groundwater. We can also use this information to make predictions based on air temperature increases in the future. So this is a map on the right showing temperature monitoring sites and predictions based on how much of an air temperature increase would be needed at any one location for the stream temperature to no longer be suitable for brook trout. So we're starting to identify places that have very strong groundwater influence and will buffer some very large increases in air temperature. If you look at the map and see those really darker blue dots associated with 7 or even 9 degrees Celsius increases in air temperature, we will likely see these places still have suitable stream temperature for brook trout in those cases. And I don't think any projections are that dire in terms of air temperature increases. So the good news is that suitable habitat may still be available. So the effects of climate change will also depend on community structure. So the presence or absence of introduced or invasive species can make the effects of climate change even more pronounced for native species. So in this case, I'll be talking about the presence of a naturalized brown trout population with brook trout, which is very common in New Jersey. So this is a problem because what has been shown to happen in warmer streams, because brown trout are more tolerant to slightly warmer temperatures than brook trout, suggests that there's something called interference competition by brown trout that are utilizing access to forage habitat that brook trout might use. But we know based on other research that brook trout can use warm water when brown trout are absent. So that's important because we can't necessarily manage for air temperatures, but we can manage for the absence or presence of brown trout. So in this case study, which was started by the Bureau of Freshwater Fisheries biologist Sean Krause in 2017 to remove brown trout and help recover brook trout population, the bar graph shows that once removals of brown trout occurred in 2017, and starting with an average of 59 brook trout captured with every pass, we really saw an explosion of brook trout into the empty spaces that were once filled by browns. And in 2020, almost 1,200 brook trout were found present. So this kind of picture-perfect result, an application of this interference competition idea, has huge implications as a management tool to help native brook trout as stream temperatures rise. But as we remove one problem, we did identify another, which is related to more extreme precipitation events and management of storm water flows. So we're also using our stream temperature monitoring network to capture unnaturally large increases in stream temperature. And it's helping to identify problem areas that we may or may not have infrastructure in place to help mitigate these issues. So the blue arrow on the left is pointing to a dot with a heat map indicating abundance of water temperature surge events that are associated with rainfall. And the blue arrow on the right is showing where the extent of trout is limited. Although a barrier does exist here, we still expect brook trout to exist above if these surge events were not there. But I'll touch more on that in a moment. So alterations in stream flow regimes are expected. We may anticipate longer dry periods. Drought is expected to occur more frequently, which will likely promote crowding, increase competition, physiological stress. It's also projected that higher winter precipitation will occur, and this will have a direct negative impact on trout recruitment, as this is one of the only abiotic factors that most studies agree on having a negative impact on trout abundance. And the primary mechanism is scour of trout redds or digging up trout nests. So the graphic to the right is from a study out of Virginia, which modeled this increase in winter rainfall and showed that if you focus on the bottom right, how increases of more years and more winter precipitation, we can expect the possibility of extirpation of trout from a particular stream. So precipitation extremes are expected to get worse, and this could mean more flooding that transports sediments, contaminants, and alter habitat. And as I mentioned in a previous slide, we're using our temperature monitoring network to identify storm flow surge events in our cold water streams. So I'm just going to jump over to the map, which is showing one of the most interconnected and abundant brook trout areas we have in the state, the headwaters of the South Branch of the Raritan River. But 4 out of the 5 tributaries shown on this map are showing, by heat map, storm surge events are increasing temperatures during rainstorm to at the very least 2 degrees Celsius in a 30-minute period. In one of these cases that we know of, labeled Sun V2 on the map, is not inhabited by brook trout, even though they exist above the major development at the dot that's labeled Sun V1. So in 2019, 15 sites out of 84 identified a water temperature surge during a rainfall event, defined as a 2 degrees Celsius increase in water temperature in a 30-minute period. And in 3 of those sites, we no longer have trout species present, and it's likely due to the impacts from storm flows. So just to show an example of what a thermograph from one of these streams looks like, we'll pull up the N Drake site, which can be seen on the map kind of in the northwest there. But these are the 5 events indicated by the blue arrows over top of them that had the storm surge events, and just highlighted in the red box is the most extreme case here with a 6.45 degrees Celsius increase over the course of 16 hours. So these types of events, even though they're not reaching what we define as brook trout's thermal limit, the temperature change in such a short amount of time could be enough to cause death and mortality in this particular population. We have not had the ability to go back out and check on this trout population. So just bring this full circle. In a study that was done out of Maryland, they found brook trout were almost never found present when impervious land cover was greater than 4%. However, interestingly, we have 4 sites here that I boxed in red and then highlighted in red their watershed impervious surface percent. And as you can see, they're above 4%, and they all have brook trout still present based on most recent surveys. So it's really important to note, as 2 of these streams have relatively high impervious cover of 13 and 20.8%, they also have extremely cold stream temperatures, which I highlighted blue here. So not only is strong groundwater influence seemingly important from the aspect of rising air temperatures, they may act as a refuge during extreme storm events that are causing large stream temperature surges. So this is another reason to continue to work to identify these cold water strongholds that will be the most resilient habitat to climate change in the future. And despite the impacts we're continually throwing at our fish here in New Jersey. So with that, I'm gonna pass it on to Brian. That's all I got.